So guys, now let us discuss virtual memory pages. So just like main memory is divided into frames which store physical pages, virtual memory of the process is also fragmented into pages of same size, which is 4 kilobytes. These pages are called virtual pages. So you can see that on the right hand side is the snapshot of the process virtual address space of the process in execution. Now if we divide the entire virtual memory of the process into blocks of equal size, then the virtual memory is said to be fragmented into virtual pages. So you can see that starting from the lowest address we have a page P0, then page P1, then page P2, and so on up to page number 2 raised to the power 32 minus 1. So each fragment of this virtual memory is called virtual page. And each virtual page has a number. For example, this virtual page has a number P2. Similarly, this virtual page is P3. So if the size of the virtual memory of a process is 2 raised to the power 32 bytes and the size of page is 4096 bytes, then total number of virtual pages into which virtual address space of the process is divided is 2 raised to the power 20 pages. Right? It's just simple math. Now let me test your ability of permutation and combination. So to uniquely identify a page in virtual address space of a process, we would need 20 bits, right? Because it is 2 raised to the power 20 pages. So you need 20 bits in order to uniquely identify a virtual page in a process virtual address space. Going further, since size of each virtual page is 4096 bytes, right? So 12 bits are required to uniquely assign an address to a byte within a page. Remember, every byte is supposed to have an address. So you can see that this diagram is actually a diagram which represents a typical virtual memory page. It means that this virtual page has 4096 bytes. Now every byte has an address. Therefore, you need 12 bits in order to uniquely assign an address to a byte within this page. So remember, 20 bits are used to uniquely identify a particular virtual page in a process virtual address space. And once that particular virtual page is identified, then a unique address within that page is identified using 12 bits. Now we will see in the next slide that where we will get these 20 bits and 12 bits from in order to locate a byte within a process virtual address space uniquely. So if you apply the combination of 20 bits followed by 12 bits, using these 20 bits you can uniquely locate a virtual page in a process virtual address space. So for example, let us say that using these 20 bits we locate page number 165, right? And once we locate a page uniquely in process virtual address space, we know that there are still 4096 bytes which is present inside this page. So using the remaining 12 bits we can uniquely identify that which byte are actually we are trying to access. So until now we have built up our basics so that we can gracefully conquer the concept of paging in the coming lectures.